Hello Velociraptors and welcome to my classroom. Today's video is going to work a little bit differently, similar to one you saw in the past. I want to go over the difference between theoretical and actual yield, which is stoichiometric calculations dealing with the lab. But I also want to use this time to work through several example problems that you can follow along with me. Thus, if you look in the description of this video, you'll see another PDF document with several problems. I'm going to work through each of these problems in this video step by step. I highly suggest try to answer the problems first. You might not know what theoretical or actual yield is, but you might be able to actually do a lot of the stoichiometric calculations you've done in the previous section. This is just taking it one step further. Let's get started. So again, feel free to download this practice set from the description and work through the problems before I do to kind of help you in pinpointing where you might have weaknesses in the stoichiometric problems. Now, the first problem we're going to work through is going to illustrate what this next step is in learning about actual versus theoretical. But I want to do a little bit of a review problem to work through it together to show you how to do it. So we can see this first problem here. It says, using the unbalanced chemical reaction above, calculate the mass in grams of water that can be produced when 103.7 grams of methane burns in excess oxygen. So first of all, we need to pay attention to this first keyword, unbalanced. So that means I need to balance that chemical equation. So let me zoom in here for a quick second. If it's a combustion reaction like this, I normally always balance the C's and H's first. So I can see there's 4 H's on the left. So I'm going to need to put a 2, here to get that water. The second is the the C's. Okay, so they're balanced. So let's look at oxygens now. I have 4 on the right-hand side. So I just need to put a 2 right here to balance it. So awesome. I could have taken inventory and followed it along, but this one was relatively straightforward. Now I can go ahead and begin to think about solving my problem. Now I gave you 103 grams of methane. And my question is, I'm asking for grams of water. So if I think about the process that I'm going to go through, well, okay, that means I have mass, and I'm going to write methane, CH4 here. I'm going to need to go to moles of methane, and then I'm going to have to go to moles of water, and then I'm going to have to go to mass of water. Perfect. Now let's go ahead and work out that problem following step by step. So the mass of methane, well, that is 103.7 from the problem. And I'm going to solve this using train tracks here, just because, of course, you can solve it whichever way you choose. I just think it's easier to follow along as I work through the problem. So grams of methane. So that means now I've got to convert to moles. Well, I know the relationship between mole and mass is molar mass. So the molar mass of methane, let's calculate that real quick. 12.011 plus 1.008 times 4. So that's 16.043 grams. Perfect. Now, the next thing I need to do is that molar ratio we introduced in the first video, the basics. And that's in relation to the coefficients. So on top, I want moles of water. I have moles of methane, CH4. So in order to get that, I need to look at my equation up here. And I see that water has a 2 in front of it, the coefficient 2. Methane has a coefficient of 1, and that's my molar ratio. And now the last step here is I need to go to mass of water. And I need to figure out the molar mass of water. Well, that's 1.008 times 2 plus 18.999. And I get that it's 18.015 grams per mole. Perfect. And now I just do all that math. So 103.7 divided by 16.043 times 2 times 18.015. And I get that the answer is 232.8935 grams. Now let's record it based on significant figures. Well, if I notice the top here, that 103.7, that has 4 significant figures. And the only thing I've done here is multiplication and division. So my answer should also have 4 significant figures. So that's 232.9 grams of water. Awesome. Now, something we haven't told you about this grams of water is actually representing a theoretical yield. And what we mean by that is in this problem, you're assuming, so one, we have a couple assumptions. One, we have excess oxygen, so that means oxygen has no impact on it right now. The second thing, so it means there's enough oxygen to react all the methane that's present. The second assumption is we're assuming that all that methane actually reacts and follows through with the actual reaction, and that we're going to capture all that water later. And that might not be the case. So that's why we would refer to this as the theoretical yield. So everything you've been calculating up to this point are theoretical yields, assuming that it completely reacts. And that's not always the case. So you'll see in the next problem here, it says, okay, so we actually perform this reaction, and we set up an apparatus to capture that water vapor that's produced during the reaction and determine that only 95 grams were obtained. Calculate the percent yield. Okay, so I only got 95 grams of that 232.9. So maybe it didn't react. Maybe I didn't have, maybe I lost it and it actually evaporated out and I didn't capture it back. And that's all definitely plausible because when you do these stoichiometric calculations, when you actually perform the experiment, of course, you're not going to have yields that look just like this. And sometimes they're favorable and sometimes they're not very good. They're just as good as this one here. And you need to calculate what we call the percent yield, which is basically to say, well, how efficient were you at obtaining the product that you were wanting? So percent yield here is just equal to the actual yield that you acquired over the theoretical times 100. So in this case, I only actually obtained 95 grams. I proposed that I would capture 232.9 grams times 100. So that means my percent yield is, let's see, 95 divided by 232.9. So that is 40.79 grams. Sorry, percent. Now, few things. So one, that only means that I didn't even get half of the yield that I was expecting, which is okay. That might actually happen. Sometimes your yield might be really small, and that could be due to several things. So that's totally okay. Don't expect that it has to be. The second, you also should still follow your significant figures. So in this case, it would be only based on the division of the actual over the theoretical. And we can see that since it's division, it would be the least number of significant figures. So 95 has 2 significant figures. So your answer should be 41%, 2 significant figures. And that's all that this unit is asking you to do, to add the extra step of understanding the stoichiometry of theoretical versus what you actually get in the experiment. That's it. Now, there's also several review problems in this unit to help you work through and practice stoichiometry and some of the other skills that we learned before. So let's work through a few more practice problems here. So the next one says, calculate the theoretical number of molecules of carbon dioxide released into the atmosphere. So we're going to assume that it's that same mass that we started with. So 137 grams of methane. And again, I'm going to write out the process because I think that helps. So I was given mass of methane. I'm going to need to convert that to moles of methane. And then I'm going to need to convert it to moles, this time of CO2. And then I'm going to convert it to molecules. And again, that's me thinking through that graphic and pathway of how to convert. And again, I would set up my train track. So it's 103.7, I believe. Yep. Grams of methane, CH4. Train tracks. First step again is converting it to moles. So using that molar mass, 16, I believe, 16.043 grams. Then we're converting it to moles of the other one. So I have moles of methane on top. Oh, that's not right. Moles of CO2, what I want. what I have on the bottom. And let's go back up here to stoichiometric coefficients. CO2 has a 1, methane has a 1, so they're 1 to 1. So that's easy, 1 to 1. The next step is then molecules. So I know that there are Avogadro amounts, 6.022 times 10 to the 23rd molecules in 1 mole of CO2. And that's it. So I just need to do some math here to finish out my train track. So 103.7 divided by 16.043 times 6.022, and I get that the answer is, I'm gonna write it down here just because I already have it, 3.89. Let's check sig fig. So I was given 4, 103.7, so I need 4, 3.89. Ooh, here's a good example. It's 8925 times 10 to the 24th. Molecules. Forgot what we were calculating. Molecules of CO2. Perfect. Now, this is a great example because it has the rule of 5s. So I need to round this too. And the next number is a 5. Now remember, a 5 means that I round to the nearest even number. So it's just going to be 3.892. But I also want to point out that if you're working on blend, unless the problem is specifically asking you to round based on significant figures, if it's not going to follow the rule of 5s. So if you're given a calculation, right, and you have to work through the calculation like these stoichiometry problems, blend is not that smart. So when you get to the end on a 5, just round up. But if I give you a problem that says round this based on significant figures, then that means that problem is trying to assess whether you know the rule of 5. So ensure you follow that rule there. Just a heads up. I also want to point out, so another good problem that I might ask is, instead of the theoretical number of molecules of carbon dioxide, I might have also said theoretical number of atoms of oxygen. And if I did that, I would just add one more step here. And I can see that there are 2 atoms of oxygen per molecule. So I would just multiply my answer by 2. So again, I could continue to work this out another way if I wanted to. Okay, so let's try this last one here because I wanted to pull in a little density problem, which we haven't done in a while. So this says calculate how many grams of methane must be burned in order to produce 15 milliliters of water. So one, I'm at a completely different, now I'm working backwards. So different than the first 2, I was working forward. Now I'm working backwards. So let's see here, process again. I'm starting with a volume of water. I need to convert that to a mass. Then I need to convert it to a mole. And what's my answer for? Grams. Okay, so then I'm going to need to convert to a mole of methane. Then I'm going to need to convert to mass of methane. I don't know why, but GMCH4. Okay, and again, I would highly advise about writing these steps out because it helps you remember what you need to do, especially if you like to solve it in pieces, which is totally okay too. So 15.3 milliliters. So let's go over here, 15.3 milliliters. Set up our train tracks. Long train tracks. Now, the other key piece here is the connection between volume and mass always trips students up. It's real easy. The connection piece is density. Density. And you should know the density of water. It's the easiest one. It's just 1 gram per a milliliter. Simple, easy. You got this. Always remember that. 1 gram per milliliter, the density of water. So now I'm in math. Now I need to convert to moles. Well, I know how to do that. That's just molar mass. So 1 mole is 18 point. What is it? 18 point. Let's cheat because we wrote it up here. 18.015. Let's make life easier. We're not going to calculate it again. Water. Now I need to convert to moles of CH4. So this is that molar ratio. You like how I said that? Over H2O. Let's go back up to the top. Okay, methane's got a 1. H2O has got a 2. Methane's got a 1. H2O's got a 2. Okay, molar ratio check. Last thing is I need mass. So I know that 6.0. I feel like it's 3.4, but it definitely could be 4.3. It is 4.3. Well, it was worth a shot for 3 grams. And there are my train tracks. So now I just need to plug that into my calculator. So I've got 15.3. See here, 15.3 divided by 18.015 divided by 2 times 16.043. Almost put 3-4 again. Now, significant figures. My answer gave me 3, 15.3. So my answer needs to have 3. So it should be 6.81 grams of methane. Perfect. And now we know how to answer this problem. In a quick recap, we've worked through different example problems, continuing to practice stoichiometry. How do we predict? How do we know how much we're going to produce? The only additional thing that we've added to the basics is the calculation here of percent yield. So when we're using stoichiometry in terms of an experiment, because remember, all the problems we've done up previously are theoretically how much we're going to produce. But when we actually do the reaction, we're probably not going to get that amount. And there are several reasons why we might not get that. Great work, Velociraptor. Now you've worked through all the nuances associated with stoichiometric calculations. You only have one more topic to discuss in terms of them, and then you've mastered it. Great work, and thanks for tuning in.